Hi students, I love you. Welcome to Suneel Engineering Academy. I am Sunil Kumar Bandaru. So many students requested that, sir, please start basic electronics through topic wise MCQs. So from today onwards, we are going to discuss basic electronics. Okay, if you have not subscribed this channel, please click on subscribe button and also please share these videos to your friends. Let us start the session, guys. Yes, coming to the first question. In the following, which is highest occupied band? Conduction, valency, energy band, and none. So in these two, valency band is highest occupied band. Is considered as highest occupied band. It is never empty, guys. Never empty. Why? Because it is filled with valency electrons. Filled with valency electrons. Valence electrons are nothing but the electrons which are present in outermost orbit. If you take any element, it has outermost orbit. In that some electrons are there. So valence electrons are always there. So it is never empty and you can say highest occupied band. So for example, if you take any one element, let us take silicon, atomic number is 14. So then 1s2, 2s2, 2p6, 3s2 and 3p2. So here what is the outermost orbit? The outermost orbit is the third orbit. In this third orbit, how many electrons are there? 2 plus 2, 4 valence electrons are there. 4 valence electrons are there. Okay. So if you can consider any element, the outermost orbit having some electrons always, so it is never empty and highest occupied band. In the same way, conduction band is filled with conduction electrons. It may be empty, or we can also say it is lowest occupied band. Very important question, guys. May be empty. Why? Because some of the elements may not participate in the conduction, so it may don't have conduction electrons. It is filled with conduction electrons, the electrons who participate in the conduction. Okay, for example, diamond may not participate in the conduction, that means may not allows the electricity. Okay, it don't have any conduction electrons. Okay, that means free electrons, it don't have free electrons, so maybe empty also. Okay, so highest occupied band is valency band, conduction band is the lowest. Coming to the next question, guys. In the following, valence electrons are bound tightly. Whenever the valence electrons are bound tightly, they may not allow the electricity. Which are not allows the electricity? Those are insulators. So we can say insulators, the valence electrons are bound tightly. Coming to the next question. In which of the following has least number of or no free electrons? Least number or no free electrons. Okay, in case of insulators, we don't have free electrons. So whenever there is no free electrons, then there is no electricity. Okay, so if you can consider any element, whenever we have some free electrons, the flow of those electrons, we have the current. Okay, for example, in our home, any one person is free, so we are always saying the work to that person only. Then he will move from that one from home to market or market to home, like that. That roaming, that movement is nothing but you can say current. So if we don't have free electrons, there is no flow of the current. Okay. As temperature increases, what happened to the resistance of semiconductor? So in case of conductors, the temperature coefficient of resistance, alpha is considered as temperature coefficient of resistance. It is positive. Positive in the sense R at T degree centigrade is equal to R naught into 1 plus alpha T. If this alpha is positive, then R at T degree centigrade is greater than R at 0 degree centigrade. That means as temperature increases, R T, T degree centigrade will be increases. That means as temperature increases, resistance will be increases. Okay, so that's why conductors are considered as positive temperature coefficient of resistance. Okay, in case of insulators or semiconductors, this alpha is negative. Whenever it is the negative means decreases. So that means as temperature increases, the resistance is decreases. So can say negative temperature coefficient of resistance. Okay, as temperature increases, the resistance will be decreases. So the answer is option B. Okay, as resistance decreases, then what happened to the current? Current will be increases. Okay, this is for pure semiconductor or intrinsic semiconductor only. For extrinsic semiconductor, that is different. Okay, coming to the next one. Extrinsic semiconductors are also act like a conductor. So those may have PTC, positive temperature coefficient of resistance. Don't worry, we will discuss those questions also. Coming to the next one. In intrinsic semiconductor, Fermi level lies dash. Fermi level lies dash. Here, in case of semiconductors, these are two types. One is pure and second one impure. Impure in the sense some impurities are added, some other materials are added, then it will become impure. Pure semiconductor is also called as intrinsic. Impure called as extrinsic. In this extrinsic, if you add p-type impurities, it will becomes p-type semiconductor. N-type impurities, it will becomes N-type semiconductor. Okay, so in case of intrinsic, the number of electrons, concentration of electrons is equal to concentration of holes. Both concentration is same. So whenever the concentration is same, then the Fermi level lies in between. Okay. So if you can consider it is a conduction band, always make conduction band on the top, valency band on the middle, at the bottom. Okay. So whenever the concentration of electrons and concentration of holes are same, or number of electrons is equal to number of holes, then this Fermi level may not attracted to any of the band. It will be in the middle. It will be in the middle. Why? Because here also same, here also same. So that's why it is in the middle place. We know very well, whenever we have equal and opposite force, that body is at standstill. Okay. So for example, if you have two jobs, what is conduction band job and valency band job? Both salaries are same. Okay. Then you are in the dilemma. You are in the middle. If conduction band is giving more salary, you will be attracted to the conduction band. If valency band gives a more salary, you will be attracted to the valency band. Correct? So in the same way, conduction band we have the electrons and valency band we have the holes. If the number of holes are more, it will be attracted towards the hole. If the number of electrons are more, it will be attracted towards the electrons. All of you getting idea about the Fermi? Okay. So this Fermi will be attracted wherever there is a more number. Okay. So intrinsic, both are same. Both are same means it is in between CB and VB. Okay. Coming to the next question. Energy gap at 0 Kelvin for germanium. This is the very important question, guys. Here energy gap is inversely proportional with the temperature, guys. That means as temperature increases, energy gap is decreases. Very important relation. Okay, so if you can consider for 0 Kelvin, in case of germanium or silicon, the energy gap for germanium at 0 Kelvin is, what germanium is 0.785 electron volt. Whenever this temperature increases from 0 Kelvin to 300 Kelvin, that means it will become room temperature. Then energy gap, as temperature increases, energy gap is decreases now. So it is 0.72 electron volt. Clear? So generally we are considering room temperature value, so that's why energy gap is considered as 0.72 electron volt. In the same way, silicon at 0 Kelvin 1.21 electron volt. As temperature increases, energy gap is decreases, so 1.1 electron volt. Okay, clear? All of you. So many students having doubt in this now. So temperatures for 0 Kelvin and 300 Kelvin. So note down these points. These are very important. Here they are asking 0 Kelvin. So high value 0.785. So the answer is option D. Okay. Coming to the next question. Energy gap at 300 Kelvin in case of silicon. In case of silicon, 0 Kelvin 1.21. 1.21, and for 300 Kelvin it will be decreases 1.1 electron volt. So the answer is option B. Coming to the next question. In the following, which is p-type impurity? Students, these type of questions are very repeated and very important in all the competitive examinations. What are the p-type impurities, acceptor impurities, n-type impurities, donor impurities? Okay, so I will give a small remembering trick to get idea on this. Okay, all of you listen carefully. P-type, n-type. Okay, so just remember in this method. P-type, P for P, acceptors. These are acceptor impurities. Okay, P for P. Here N for N, donor impurities. These are donor impurities. All of you clear? P type are acceptor impurities, N type are donor impurities. Generally we know semiconductor, either silicon or germanium, have how many valence electrons? Very important question. They have valence electrons are 4. Okay, valence electrons are 4. So in this case, if we add plus or minus 1 for this, then we can get higher number of holes or higher number of electrons. That means we have to add 4 plus 1 means 5, 4 minus 1 means 3. So we can add trivalent or we can add pentavalent impurities. Then we can get uneven, that means not equal number of holes and electrons. Okay, so here these are acceptors. Acceptors means ready to accept. Whenever they are ready to accept, whenever they have less electron, they ready to accept. Okay, for example, silicon or germanium have 4 valence electrons. If it has 3 valence electrons, then only they accept now. So these are trivalent. P-type impurities are, or P-type are trivalent. So trivalent, so that's why they are always ready to accept. Ready to accept. In the same way, donor, they are ready to donate. Ready to donate means always having some higher. So pentavalent. These are pentavalent. So 5 valence electrons. All of you clear? P-type trivalent, N-type pentavalent. Now coming to the example. Coming to the example. For P-type, the example is a big tree. Try na. Try for a big tree. So try for 3. So A for aluminium, B for boron, I for indium, and G for gallium. Okay, so these are the examples of P-type impurities. And coming to the N-type impurities, pen, Bapuji's pen. Pen. Bob, who donate the freedom to Indians? Bob donate the freedom to Bapuji, donate the freedom to the Indians. So like that you can remember Bob. B for bismuth, A for arsenic, and again A for antimony and P for phosphorus. Okay, so in this way you can simply remember. And P, in the P type, P is a big hole, so majority carriers are holes and minority carriers are electrons. Okay, here N type, major N for electron, majority carriers are electrons, minority carriers are holes. We can also understand this one by the concept, but here in the MCQs discussing all the concept is taking a lot of time, so that's why I'm giving a simple methods to remember. Okay, once again guys, all of you close your eyes, just listen. We have P type semiconductors, N type semiconductors. Okay, P type, P for acceptors. So if they want to accept, there has to be less valency electrons than the semiconductor. So that means those are nothing but trivalent. So trivalent, tree. So tree means a big tree. Tree for big tree. So A for aluminum, B for boron, indium, gallium. Okay. So all these having three valency electrons. Okay. Three valency electrons. That means these silicon having 4, this trivalent having 3, so they accept one electron. Whenever one electron move from silicon to this trivalent, here one hole is created now. Here one hole is created. So many elements we have now. So many molecules we have. That means so many holes are created. So holes will be higher. So this will becomes majority carriers and remaining will be minority carriers. In the same way, N type semiconductor, N for donor. N for donor. If they want to donate, they must having one electron more. Okay, at least one electron more. So that means more than 4, that is 5. Pentavalent. So N type are pentavalent. Pen. Who donates the freedom to Indians? Bapuji. So BAP. Bapuji's pen. That is a remembering trick. BAP. B for bismuth, arsenic, antimony, phosphorus. Okay. So in this N type, what is happening? Here they are donating any that is any element if that donate the electrons, that donate one, then concentration of electrons will be increases. Okay, so then majority carriers will be electrons and minority carrier will be holes. Okay, minority carriers will be holes. This is in case of N type. So P type impurity, P type a big tree. So here A for aluminum. So the answer is option D. Coming to the next question, P type impurities. P type impurities, a big tree. Okay, so aluminum, boron, indium, gallium. Boron, indium, gallium, all given now. So answer is option D. Okay, like that you can give the answer. In the following, which is acceptor impurities? Acceptor, P type. Again, P type, a big tree. So boron, indium, gallium. So we can say all. In the following, which is N type impurity? N type, N for donor. Who donates the freedom? Bob. Okay, bismuth, antimony, arsenic, phosphorus. Phosphorus is there, so we can give the answer as phosphorus. Okay. In the following, which are N type impurities? Bob, bismuth, arsenic, antimony, all are there, so we can give the answer as D. In the following, which is donor? Bismuth, arsenic, antimony are donor impurities, so we can give the answer as option D. So if we know this simple concept, if they have given the question in any manner, we can give the answers. Okay. The P type semiconductor Fermi level lies. Just I said, this Fermi level always attracts wherever there is a more concentration. It will be attracts wherever there is more concentration. In case of P type, what are the majority carriers? Majority carriers, holes now. Minority carriers, electrons. So it will be Fermi level attracts towards to the majority carriers, towards to the holes. So here we have conduction band, here we have valency band. Okay, generally it is in the middle. for intrinsic. Okay, so in case of p type, the majority carriers are holes. Holes are exist in valency band now, so it will be shifted towards to the valency band. Okay, now the valency band having more money, so that's why it is shifted towards to the valency band. Shift to downwards, that is near to the valency band. Shift to downwards, that is near to the valency band. Okay, the same way if you can consider n type. N type majority electrons, minority holes. Okay, majority are electrons, minority are holes. So that means it will be shifted to majority carrier side. Majority carriers are electrons. Conduction band having electrons. Valency band having holes. So for intrinsic it is middle. Okay, now here the majority carriers are electrons, so it will be shifted towards to the majority carrier side. So that means it will be shifted upwards, that is towards to the bottom of conduction band. Shift upwards, that is towards to the bottom of conduction band. Okay, all of you clear? These are very important question, guys. Coming to the next one, semiconductor found by dash bonds. Semiconductor found by very strong bonds, that is covalent bonds. So the answer is option A. Coming to the next one, silicon and germanium contains how many valence electrons? I have already given silicon and germanium having 4 and 4, that is silicon having 4, germanium having 4. Gallium having how many free electrons? What is this question, sir? Whenever we are getting this question in the examination, so we feel that why they have given physics questions and all those. So here just think about this. Gallium, boron, indium, gallium, aluminium. So all these are nothing but, you can say, trivalent. Na? So trivalent means they have 3 valence electrons. So if they are asking gallium, we can directly give the answer as trivalent. Na? So no need of atomic number, no need of electronic configuration and all those. Okay, so whenever they have given the question on aluminium, boron, indium, gallium, how many valence electrons, simply you can use trivalent. Okay, in the same way bismuth, arsenic, antimony, phosphorus, you can use 5 valence electrons. Okay, 5 valence electrons. Coming to the next one. When a free electron is recaptured by hole, that process is called as. Whenever that is electron is recaptured by holes, that process is nothing but recombination. That process is nothing but recombination. Okay. Okay, students, we will discuss the remaining questions in the next session. If you like my classes, please click on like button and encourage me, and also share to your friends. If you have not subscribed this channel, please click on subscribe button. And these sessions are useful for all of your competitive examinations and useful for both the ECE and electrical students. Okay, thank you so much, guys.